In part 5, we're solving more systems algebraically, but this time using the elimination method. And again, we'll write our solution as an ordered pair. So we'll look at 5b together, but in 5a, like remember, the question I always kind of ask myself first is, if I add my equations right now as is, will a variable term, either x's or y's, cancel out and when I get my new equation? So in 5a, it jumps out to me that I have a positive 8y and a negative 8y. So that one's going to be pretty easy. We can just add them together. Let's look at 5b though. In 5b, my x coefficients don't match and they're not opposites, right? I have a -3 and a -5. And my y coefficients are exactly the same. So they're not opposites, they're exactly the same. And we really, we could either think of this as subtraction and proceed, or we could choose one equation, multiply everything by -1, and combine with addition. It's your choice. Same thing either way. I'm going to choose the latter method. So I'm going to multiply this entire equation on bottom by -1. And again, that's just that multiplication property of equality, that I can multiply both sides of an equation by the same amount. Same with division. I can add a number on both sides. I can subtract a number on both sides. Okay, so on the left-hand side, though, we have to distribute. So that's going to cause everything to get a different sign. And on the right-hand side, that -21 is now a +21. So when we multiply by -1, we're just changing the sign, and in this case, of every term. So now we're going to combine that with the -3x minus 4y equals -3. And so when I add these two equations together, I get a +2x. My 4y and -4y cancel out, so there's like 0y, which is just 0. And 21 minus 3 is 18. All right, and then lastly, just to solve for x, we could divide by 2, and we get x equals 9. All right, so now we could substitute x equals 9, or 9 for x, into either of our original equations, or you could use this equation that we got when we multiplied by -1. And there's nothing wrong with using that equation. I just would be careful that if we made a mistake when we multiplied, it's possible we won't catch that mistake if we use that to find y. So because of that, I'm going to use the top equation. Although in theory, if we didn't make a mistake, it shouldn't matter. So -3 instead of x, I'm going to substitute 9 minus 4y equals -3. And let's see, -3 times 9 is -27. So when I add 27 to both sides, we get -4y equals, what is that, 24? And then divide both sides by -4. So I'm getting y equals -6. And now a good thing to do would be to just check our work, make sure it works out. So I'm going to use the other equation. So -5 times 9 minus 4 times -6 should work out to be -21. So let's see, that's -45. That becomes plus +24. Is that in fact -21? Well, it is. All right, so our solution is 9, -6. Okay, let's look at maybe just one more. Let's look at 5c. So the bottom examples, what I notice is I don't have something really nice and easy. I don't have in either 5c or 5d a case where all I have to do is multiply by a -1. But we can multiply one or both equations, or divide both equations by a number to generate opposite terms. So in 5c, I could divide my top equation by -2. I could divide every term by -2. I could divide by +2 and just deal with the negatives as I go. Or I could multiply my bottom equation by 2. So I'm going to multiply just because, I don't know, just because that's what I feel like doing. And instead of using a positive 2, I'm going to multiply by negative 2. And that will cause my x variable to cancel out, right? So I'm going to do this on both sides of the equation. That looks like it's subtracting, but that is times a negative 2 there. So when I distribute, I get negative 12x plus 10y equals negative 22. So it looks like something interesting is going to happen when we combine these two equations with addition. I'm leaving the stuff in between. Well, positive 12x and negative 12x becomes like 0 or 0x. Oh, but our y's also cancel out. Negative 10 plus positive 10y is like 0y. And positive 22 plus negative 22 is also 0. So we get a statement that says 0 equals 0. And since that is a true statement, that means that we have infinitely many solutions. So that also means that if those two equations are the same, they're just in a different form. All right, had we gotten a false statement there, like if I'd gotten something like 0 equals 12, then I would know that there are in fact no solutions. So lastly, the very last thing, it says in the space provided, just sketch 3 graphs of systems that have 1, no, or infinitely many solutions. I'm gonna be so lazy that I don't even draw a coordinate plane. So if I have one solution, that just means I have 2 lines that intersect. And remember that when we're solving this using algebra, or sometimes we say solving analytically using substitution or elimination, I'm going to get a value for x, I'm going to get a value for y. When we solve a system graphically that has no solution, that is when we get parallel lines. And that's also going to be when I solve analytically, where I get a false statement. So oftentimes like our x's and y's will cancel out and we'll get something like 0 equals 4 or something. Well, that's not true. 0 does not equal 4. Lastly, infinitely many solutions. We said when we graph this, that both of our equations will be like on the same line. They'll cross the same line. And we said analytically, we know this happens when we get a true statement. So maybe something like 0 equals 0, or they could be numbers. I think one in class we got like 8 equals 8. So if we get a true statement, we have infinitely many solutions.